All right, welcome to day 25 of CN Software Tools class. We are in what is, for me, the fun part of the semester. We get to talk about C++. I like a lot of that stuff from C. I certainly like being able to program that close to the hardware, but when I'm actually writing code for myself, I mentioned I coach the competitive programming teams here at NC State. And usually when I'm trying to solve competitive programming problems, trying to write something really fast, C++ is the language I pick. It gives you a lot of the advantages of an object-oriented language like Java, but it can be a lot more concise than Java, which can save a little bit of time in writing code. That's just by way of introduction. Here's where we left off on Tuesday when we were talking about C++. We just finished, what had we just? We had just finished talking about default parameters. And we're just covering, really, I tried to cover C++ topics that don't involve object orientation first. I think there's a lot of nice features in the language that don't have anything to do with objects. And then after this, we'll talk about some of those object-oriented features when we get into the Lecture 25 material. I mentioned that C++ has a mechanism kind of like Java's package mechanism, a way of hiding names in what C++ calls namespaces. And this makes it so that you can manage things like collisions for global names. You can avoid them by having different parts of a project or having standard library features hidden inside a namespace. And when you include things like IOStream, you get access to a bunch of symbols, a bunch of function names, a bunch of type names, some object names like cout, but they all live inside a namespace called std. We've been avoiding having to talk about this by putting that using namespace std near the top of our code. I think the current, even though that's a nice shorthand for giving you access to all that, I think the current reasoning is, well, that's probably a bad way to write a non-trivial program. If you wanted to manage a bigger program, you might want to be specific about what symbol names you wanted to use. And here's how you could do it. Kind of like putting a package prefix in Java. The real name of cout, or at least its full name, is std::cout. This is the name, and the std is the namespace it lives in. And you can see here a new operator that was introduced by C++. It's called the scope resolution operator, and it's 2 colons in a row. I think whenever you have to extend an existing language, you have to kind of find syntax features that no one was using or that they couldn't have legally used. Because if you want to introduce a new operator or a new reserved word in the language, you want to pick something that's not going to break existing code. So in existing C, no one would ever have been using 2 colons in a row. It wouldn't have been syntactically legal. So they made a new operator that looks like that. Again, it's called the scope resolution operator. This job is done by dot in Java. Dot does a lot of different jobs in Java. But if you got a package prefix and then some name defined in that package, you use colon to be specific about the package that a name is defined in. And here you can use the scope resolution operator for this. It really lets you refer to things in a particular scope, and a namespace is treated like a scope. So if you didn't do the using namespace thing and you wanted to talk about cout, you'd have to give its full name, std::cout, std scope resolution operator cout. And then the same thing for endl. It's also an object, or really a variable, a global name defined in the std namespace. Namespaces aren't just for code that's part of the standard library. You can define and use them yourself, and that makes sense because if you were implementing a large project, you'd want to be able to organize it or at least put all of your code into one or more namespaces. Here I'm showing how you can do this yourself. Up at the top, I define a couple of things, a variable val, which is just a global variable, and a function f, and I didn't put them inside any namespace. And then I made my own namespace. Here's the syntax for it, namespace, and then whatever identifier you want. And then inside curly brackets, you can define any variables you want. They're like global variables, but they're defined inside this namespace. So they won't collide. So like here, I deliberately make another variable val that has the same name as the one up here, but they don't collide. For the linker won't complain about this because this one is just plain old val and this one is val inside this namespace, inside my namespace. Same thing for function f. And then down here in some client code, let's say this code at the bottom is part of main. I can access both of these things. If I'm in a function main and I call f, well, main is not inside any namespace. So unless I say otherwise, I'm going to get the f defined up here. If I want to be specific and say, oh, I want the function f defined in this particular namespace, I just have to stick its prefix or its namespace in front. So this will call the f defined in my namespace. Even inside this function, I can decide what things I want to access. Like if I print out val, well, if I don't say anything otherwise, I'm going to get the one in the narrowest surrounding scope. So I'm going to get the one defined in my namespace. If I want the one up here, I can use the scope resolution operator to get it. And this is a little weird, but if you don't put anything to the left of the scope resolution operator, you're going to get stuff defined in the global scope or not in any namespace. So this will print out 3. I'm getting the version of this variable, or at least I'm getting the val variable defined at the global scope. So this is really all the syntax you need to define and use namespaces. You can define things in a namespace in different parts of your code. You don't have, like here, I'm putting it all in one place, but you can define stuff in a particular namespace in one piece of code, and then you can leave that namespace, and then later in your code, you can define other stuff that's in that namespace. So you don't have to put it all in one place. Questions about namespaces? All right.
Just for clarity,
yeah.
So the namespace is kind of like a struct inside of a header file.
You could put this in the header file. Here, I'm pretending it's just part of an implementation file. So I guess, let's say you wanted to define a struct, but you didn't want it to be at the top level of scope because let's say we were going to call it node. And lots of people want to make a struct called node. So to avoid collision with that, you could hide it in a namespace. The type definition could go in a namespace declaration like this. And then at the end, and you could put that in a header. And then at the end of the header, you could leave that namespace. And then in your implementation file, you could go back into that namespace and say, oh, that node that I was using, here's code that uses it, or here's other code that's inside that same namespace. So this could go in a header. If you had types in a header, and certainly in the standard library, there's a bunch of stuff in the headers that say, oh, this is part of the STD namespace. But then in the implementation files for the standard library, they also define functions that are part of the STD namespace. So the syntax for this looks kind of like a struct, but you're not really defining a type. You're just saying all the stuff inside these curly brackets is part of this particular namespace.
Okay,
Did I explain, or let me know if I didn't explain what I was talking about or what I was trying to talk about. All right, I was about to say, this is one of my favorite features of C++. It is a new type operator for declaring reference types. Over on the left, I'm showing how you use it. So it is a type operator, so you use it to define new types. And you use it kind of the same way you use star. Star is how you define types that are pointer types. Ampersand is how you define types that are reference types. Reference types are a lot like pointer types, but with simplified syntax. Let me tell you what's going on the left of this slide. And then on the right, I'm showing how you can think of it. Like I said, reference types are kind of like a simplified syntax for working with pointers. Over on the left, I declare a variable named I, and I give it a value, nothing fancy there. On the next line, I make a variable j, but I make it a reference to an int. That's how you can read the ampersand when you're reading types. J is a reference to an int. And I set it to I. Because it's a reference, it doesn't get a copy of i's value. You can think of it as just another name for the variable I, kind of like it was a pointer to I, but I don't have to use the pointer syntax when I'm accessing it. So think of J as an alias for I, or another way, sorry, my phone is giving me a weather alert. And I don't know how to stop it except by powering off. I'm going to go carry it to another part of the room. I'll be right back. All right, sorry about that. All right, on the left, I was trying to make the point that references are like creating aliases for values. J is just another way of getting to the variable I. So if I set I to 30, well, now I is 30. If I assign J to 35, well, J is just another way of getting to I, so that sets I to 35 via, you could think of it as another name for I. Over on the right, I'm showing how this is really implemented, or at least I'm showing how you would have done the same thing in C. In C, in plain old C, I could have made a variable I could have made J a pointer to I. Well, to do that, I would have to make it a pointer to an int. And I would, if I wanted to point to I would have to give it the address of I. Down at the bottom, I'm showing, well, you could assign I to 30 just by assigning it, giving it a value of 30. Or if you wanted to get there via J, well, you could dereference J, and then you've got, then you're talking about what's in I. And you could assign 35 to that, and that would also change what's in I. The picture over on the right is what references do. In C++, when you say, I want J to be a reference to an I, internally, the compiler is using J to keep up with the address of I. But you don't have to dereference J to change what's in I. You can just use it directly. And you don't have to take the address of I to make J point to the same thing. That all happens internally. This is why I say it's kind of a simplified syntax for working with pointers. But this simplification is awfully handy in a few different places. In particular, if you want to define a function, like previously we've defined a swap function for swapping two variables. Here I made the same thing, I just called it exchange here. Instead of saying exchange takes a pointer to an int A and a pointer to an int B, I'm using this reference type we just learned about. Inside the function, when I talk about A, I'm really talking about what it refers to. Same thing for B. So inside the function, I don't have to dereference, at least I don't have to use the dereference syntax whenever I want to talk about what A and B refer to. That's what references mean. So I can just talk about A, and since it's a reference to an int, the compiler knows I'm really talking about the thing it refers to. So my syntax inside the exchange function gets a little simpler. When I say gets a little simpler, I mean if you compared this to a function that took two pointers to an int. If you wrote that function, you'd have to say star A here and star B whenever you accessed what these things point to. But the syntax gets a little simpler here. That's worth a little bit, but I think it's worth even more for the caller to this function. If you did this with pointers, the caller would have to know to pass the address of X and Y, the two variables they want to exchange. But here, it's just like the syntax back here. If I'm making a reference to an int J, and I want it to refer to the same thing as I want it to be a temporary alias for I can just say that starts out with I. And internally, the compiler knows, oh, you want to take the address of I and use J to keep up with that address. For the caller, they don't have to put in the ampersand. When X gets assigned to A when we call this function, A is automatically an alias for X. Same thing for Y and B. So this means the caller doesn't have to be as smart. They don't really have to know the difference between a function that takes a reference to something as a parameter and something that just takes a copy of that parameter. They can write the code to call it the same way, and then it's really the person who defined the function that decides how the parameter gets passed to it. So this simplifies the syntax a little bit. Internally, it's still doing the same thing with pointers, but we don't have to, the caller doesn't have to know that when they're calling the function. This could be handy when you're, we ended, I think it was our previous lecture, talking about how if you had a struct and you wanted to pass it to a function, often we pass it by address. So we don't have to copy the whole struct, but that meant the caller had to know to pass the address of a particular struct. Here with references, we can do that same trick with simplified syntax. So if I've got a struct and I want to pass it to a function, but let's say I don't want to make a copy of it, I can say I take a reference to whatever that struct is, and then inside the function, I can use that as if it was an instance of that struct. So I can use the dot operator for getting to its fields rather than arrow, even though what's really going on is I'm not making a copy of the struct, and the parameter to this function is really internally. It's implemented as a pointer to an instance of this struct. I just don't have to use the pointer syntax inside the function. Backing up a slide, just like here. If I had references to int, I don't have to dereference them every time I want to get the int they refer to. So here, my syntax is a little simplified, but even more importantly, when I call this function, I don't have to be smart enough to pass the address of A. It was really the person who wrote the function that decided when you give me a parameter, I'm gonna take that parameter by reference rather than copying the value of that parameter. Just like with pointers, I can still stamp this with const to say, well, I want a reference to your struct, but I promise I won't change it. I only want to look at it. And if you put const here, the compiler will complain if you try to modify anything in this struct. Another place where references are handy is return by reference. This lets you return a value that you can then use either to look at that value or to change it. It's like you're returning, well, let me talk about this example and this might help it make more sense. Let's say I had a global variable that was a list of names along with a value for each name. And that's what I printed out here. So maybe Mary is my first name with a value of 42 and a bunch of other names on my list. Let's say I wanted you to be able to look up names and get the value associated with them, but I didn't want to just give you a copy of that value. Let's say I wanted to make it so that you could either use that value if you wanted, or you could change that value if you wanted. That's what return by reference lets you do. I could implement a lookup function. You give me a string you want to look up. I'll go through the list, match the name that goes with that string, and return the value. So for Mary, I would return 42. For Bob, I would return the 17. But if I return it by reference instead of by value, then just like returning a pointer, you can use that reference to either look at that value or change it if you want. So if you want to look up Mary and just get a copy of her value into variable X, that works fine. Or if you want to look up Bob and then assign some other value to Bob, since you returned this 17 by reference, internally you're really returning a pointer to it. And even though you don't have to use the pointer syntax, you can assign to that returned reference, and it'll sneak in and change this 17 to 35. Because again, even though we're not having to use the pointer syntax, what's happening internally is when we return by reference, we're returning, internally, we're returning a pointer to that int, and then you can assign to what that pointer points to without having to dereference it. So again, the point I've made a couple of times is it's kind of like being able to use pointer syntax with a simplified syntax. The simplified syntax costs you one thing, and I'll go back a couple of slides to try to describe this. So the consequence of using this simplified syntax is once you've made the reference J, you can't make it refer to anything else. When you're using the pointer syntax, well, if you make a pointer j that's a pointer to an int, you can either change the int it points to or dereference it and change the contents of I here, or with pointer syntax, you could make j point somewhere else if you wanted. Well, with the reference syntax, because it's simplified, there's no way of making j refer to something else after you've created it. Here, j starts out as an alias for I, and if you assign to j, you're really changing I. There's no syntax for deciding, oh, I want j to refer to somewhere else. You can only do that at the time when it's declared. If you want to be able to change what j refers to, you still have the pointer syntax to let you do that. But in cases where you always, for j's lifetime, you want it to be an alias for something else, the reference syntax is a simplified way of saying that. I've tried to illustrate here places where I use references. All the time it gets used as a way of passing parameters to a function, either parameters of a primitive type or a struct. Return by reference actually gets used a lot for making data structures that are easy to use. You can look up elements of a data structure and assign to those elements, and we'll see some syntax for this a little bit later today. Another place where I use this a lot is taking a short name for a complicated expression that I evaluate. If you're building a data structure, and you kind of did this in project 4, you might have an array of something that you look up an element, and then you may look in a field of that. And that may be a pointer to a struct that has another field. And if that thing is an array, you might look up an element in that. So this long, sort of complicated expression, maybe you have to use this in a couple of places. Instead of having to copy this syntax and use it over and over again, or like I've seen some people do in their code, sometimes they copy that value and then put it back later after they've modified it, which seems a roundabout way of doing things. Instead, what if you want to use this thing more than once? You could just take a reference to it. I made X refer to whatever this evaluates to. And then if I want to print out what that thing was, I can use X. If I want to sneak in and change it, I can use X. So you can think of using a reference as a way of being able to get a shorthand name for a thing that you've previously evaluated. And then you can use that name later as a way of getting to that thing. Internally, you're just taking a pointer to it, you're taking its address, and then whenever you try to look at it or change it, you're just using that pointer. So it's not really using a copy of the expression, it's just using the result, a pointer to the result of whatever that expression evaluated to. I use references all over the place. I find them very handy. I wish other languages had things like this, and some of them do. Java doesn't let you do this all over the place, but I find it pretty handy in C++. Questions before we move on?
I have a question, or actually like a couple, actually. Can you do, my first question is, can you do pointer arithmetic
With references?
Like if I did X++ with this, would that make X, like after you have X equals 18, would that make X equal 19? Or would that make it the next element?
Yeah, so my quick answer is when you decide to use references, you kind of give up that pointer arithmetic syntax. I hadn't thought about that. But now, whenever you talk about X, you're talking about the thing it refers to. So if you say X++, that 18 is going to become a 19.
Well, can you use the ampersand operator on a reference to get the original?
Yes.
So I could do that.
Yeah, I mean, it's kind of weird because you notice they're trying to reuse a limited set of symbols to mean different things. So we use ampersand to declare a reference variable, but we still also use it to mean, give me the address of that thing. So if later you said, give me the address of X, you're really going to be getting a pointer to whatever this thing evaluates to. You're going to be getting the pointer that that's stored internally in that reference. Other questions?
Yes, sir. So going back to the slide. lookup Mary, the one that was.
Yeah.
So that X value there, that's actually a pointer to that address. So if you modify X, is it going to change that the value of Mary there?
X isn't a pointer, but whatever lookup returns, internally, it's implemented as a pointer. But if you call lookup and then you say, I want to copy that to X, which is what you're doing in this assignment, well, X isn't a reference to what lookup returned. It's just a copy of it because it's just a plain old int variable. If you stuck an ampersand in front of this X, then X now refers to the same thing that lookup returns. And then changing X would change whatever lookup returns. But because I made X a plain old int here, it's in this initialization. It's going to get a copy of this 42 here.
Okay, thank you.
There was another question. I know two of you were talking at once.
Oh,
All right,
sorry.
Go ahead.
My like every now and again it'll like freeze a little bit on my screen.
I understand.
So, but my question was, if you make a reference to the first element in an array and then you call size of that on that reference, does it evaluate to the size of the pointer, or does it evaluate to the size of, if it was an array of ints, would it evaluate to the size of an int, or would it evaluate to the size of the whole array?
I am making up this answer, but I feel pretty good about it. If you make some variable X a reference to the first element of an int array, then X is going to behave like an int. And I think if you say size of on it, it's going to give you the size of an int. So internally, references are implemented the same way we would have with pointers. But they tried to make their syntax work as if they're just another value of whatever type they refer to. So I think if you said size of on a reference, like backing up a slide or two, yeah, here's our first slide on references. Here, I think if you make int I and j a reference to an int, if you asked about the size of j, you're really asking about the size of the thing it refers to. So I think it's going to say 4 on the common platform, the size of an int, rather than 8, the size of a pointer. I'm guessing on that, but I feel pretty good about that guess. You can try it if you get bored during lecture, and let me know if I'm wrong. I don't mind the questions on references because, like I said, I find them awfully handy in C++. Other questions? All right. A couple more things before we finish up the material we should have done last Tuesday. C++ supports a template mechanism, and this is kind of like generics in Java, except when you define a template, you're really defining sort of a pattern for a piece of code, and the compiler will create multiple instances of that pattern based on how you use it. In Java, when you define a generic class, the compiler is really only implementing one version of that class. It's just letting you use it with multiple types. It's kind of using the inheritance hierarchy to do the generics. But in C++, when you define a template, you're kind of defining a recipe that the compiler can use. I normally say things like to stamp out different copies of the templated code. I've got an example here to try to help this make sense. So if you want to make a template, there's a new reserved word template. And then kind of like Java's generic mechanism, after the word template, you can describe as many type parameters as you want. So inside angle brackets. So inside less than, greater than, those, they're using those as kind of like parentheses here. Inside the angle brackets, you put as many type parameters as you want. To declare a type parameter, it's type name and then whatever name you want. And then the template covers just the next definition. So if you wanted a bunch of functions that each had a type parameter, you'd have to say template in front of each function. If you wanted, later we'll see if you wanted something like a class or a struct that had a type parameter, you could put template in front of that struct, and then it would cover the whole struct definition. Here, I'm just doing it for a function. So this function exchange has a type parameter t, and you can think of that as standing for any type that you could substitute in there. So int or double or some struct if you wanted. Here I'm going to define, what I'm doing is I'm defining a generic exchange function. It'll work like swap, but not just for one type, for any type you want. Well, if I'm going to make exchange so it works for any type t you want, the two parameters both have to be of type t. So you have to give me a parameter A of type t, a parameter B of type t. I made them both references to t so that you could pass them in and the function could modify the thing they refer to. I won't back up in the slides, but this is the same trick we did before. I'm just sticking in a type parameter here. So this exchange would work to swap any two values of type t that you wanted. For whatever parameters you pass in, A and B, they're going to be passed by reference. Inside the function, well, I need a temporary variable for holding what was in A. I can use t to declare that for whatever type t you're using on. And then the rest of this is exactly what you expect. It's the code to swap A and B using that temporary variable. So here's a template version of Exchange. How do you use it? Well, to show off how you can use it, I make a couple of variables A and B of type int, and then and a couple of variables X and Y of type double. And then I use the same function to exchange both of those types of variables. When you call exchange, you can specify the type parameter you want to use it on. So here I'm saying I want to call exchange, and I want to use a type parameter of int. When you do this, you can think of this as instructions to the compiler to say, I know there's a function named exchange that takes a type parameter t. I want you to build me a version of exchange where int is plugged in place of t. So the compiler, you can think of it as running off and saying, all right, I'll stamp out a copy of exchange. I'll create a copy of exchange where t is int. So it'll plug in int for t here, and for t here. So this is what we mean by template instantiation. It builds a version of exchange that works for int, where int is plugged in place of t, everywhere t shows up in that template definition. And sure enough, if you plug in int as a value of type t, you get a version of this function that works for ints. So it can swap A and B. The compiler tries to be smart about this. So if it has already made a version of exchange that works for int, it doesn't make another one. It just uses the one that it's already made. So it kind of keeps a list of all of the instantiations it has done for templates. And then if it has already instantiated a version of this function for int, it just reuses that. And the compiler tries to be smart about the type parameters by inferring the types if it needs to. Here I'm being explicit. I'm saying I want you to make a version of exchange that works for type int, but if you leave that out, the compiler will try to figure it out. If you say call exchange and you pass in two doubles and you didn't say what type you want it to be, the compiler is smart enough to do, again, what's called type inference. It will look up and say, oh, I've got a definition of exchange that works for two parameters that are both of the same type t. You're giving me two parameters of type double, so I could make this exchange work down here as long as I plug in the value double in place of t. And wherever it can, the compiler will do type inference so that you don't have to specify the type as long as it's unambiguous. And for a function like this, most of the time, client code would not specify the type parameter. It would just let the compiler figure it out, again, using what C++ calls type inference. Lots of languages do type inference like this. I think I mentioned, just to fill out how the template mechanism works, you can have multiple type parameters if you want. So here I'm pretending I'm using a template declaration with two type parameters. You just separate them by commas and you have to use different names for each parameter. And then here I'm using that to define a function that takes a reference to whatever type t is as its first parameter and a pointer to type v for the second parameter. This template mechanism is, again, kind of like what generics do in Java, except every time you specify a different type parameter, the compiler goes ahead and creates code with that type parameter plugged in. This gets used all over the place in the standard template library in C. That's kind of like Java's collection framework. Just like the collections framework in Java uses generics all over the place to let you make things like array lists of whatever type you want. The standard template library in C++ uses the template mechanism to let you create data structures for whatever type parameter you want to use. We will see this again in a moment. Questions before we move on? One more, go ahead.
Sorry. Do standard library functions in C++ that would have used void pointers in C now use templates?
Well, they still, I mean, all that stuff from C is still there, and it's still like sort is still there, and it still uses actually qsort. It still uses void pointers as a generic pointer. But yes, the new stuff that they created for C++ uses templates in place of void pointers a lot, with the idea that if you tell me what types you want this to work for, I'll just create a version of this function for that type. And I find that a lot easier to use. I can still use both of them, but the template mechanism, I think it simplifies some of the syntax. Oh, and I forgot this bullet right here. The reason I was calling this function exchange instead of swap like we've called it before is because C++ already has a generic swap. The thing that we were doing back here with exchange, we didn't really have to do that because the standard library, the standard template library already has a generic swap function that pretty much is exactly like what we did here. So they already thought of this. I just used it as an example to illustrate how templates work. Other questions? Here's one last handy trick in C++. I mentioned C++ supports type inference. And this is handy. It means when you're using templated things, you don't always have to specify the type parameter. You can ask the compiler to figure it out. And it lets you use this type inference mechanism when you're declaring variables using the auto keyword. You remember auto in C, in plain old C, you can use this to declare local variables, and it means automatically create this variable whenever I go into this function. But it almost never gets used because that's what local variables do even if you don't say auto. So it was kind of a wasted keyword in the language. C++ 11 resurrected this keyword, or at least they said, oh, let's let this do something new. You can use auto as part of a variable declaration. And when you say auto, you're saying to the compiler, figure out what type this needs to be using your type inference mechanism. And that's what I'm illustrating here. In the code at the bottom, I'm declaring a bunch of variables, but for their types, I'm just using the word auto. What that means is you can think of that as meaning for the compiler, figure out the type of this thing. Well, here, based on how I'm initializing it. So in this type, so auto isn't really a generic type. It just means pick a type at compilation time, pick a particular type based on what I'm assigning this thing to. So in this top example, well, 25 would be an int. So A would get, even though I said auto for its type, the compiler would say, oh, A must need to be an int because that's what you tried to put in it. X, well, I didn't specify its type, but the value I'm giving it would be type double. That's what floating point values are by default. So X would actually get a type of double. I didn't really need auto there, but for fancier types like a function pointer, up at the top, I define a function that takes an int and a reference to a const double and returns long. And I could define that function pointer type, or I could use auto to let the compiler figure it out. Here, F is going to get that function pointer type because that's what the name of the function evaluates to. Here, if I call that function, it evaluates to an int as the return, to a long as the return. C is going to get type long because that's the type this function returns. You can use this wherever you want to avoid having to specify complicated type names. And pretty soon we'll see you can come up with some awfully complicated type names in C++, just like we could in C. We don't really need auto for this, but it's awfully handy for shortening our code, especially when the type that we need is uniquely determined and the compiler can figure out how to say that type name rather than us having to write the code for that type. I claim I still could have written the code myself, but I can save a lot of time by letting the compiler figure it out for me rather than having to specify the exact syntax for that type. So like I'm saying on my slide here, this is really just avoiding it's a way of being lazy in writing our code. But when the types get long and complicated to write down, it's nice to be able to be lazy. Questions before we move on to the next batch of slides? I find auto very handy when I'm writing, when I'm trying to avoid writing complicated type names in C++. This wasn't in the original specification, but in C++ 11, they added it. And that's one reason we're targeting C++ 11. All right, like I said, we're going to cover as much C++ as we can. And on day 2, we're going to start using classes that other people wrote. We kind of did that a little bit with the input and output streams with ifstream and ofstream, but we're going to get a lot of mileage out of a couple of classes we'll see today. And the first one is C++ has a string class. It is not a primitive type. It's a class. It has, later we'll see, it has methods, or in C++, they call them member functions, like you would expect for a class. But they tried to make it so that you could use it as if it was a built-in type, as if it was a primitive type. And that's what I'm going to try to show here. You can still use char pointers for strings. You can still use character arrays to store strings. But this is another option for storing strings. It's not the same as a character array. It's a class. But for a lot of things, this is a more convenient way of keeping up with a string and passing it around between your code. So string is an object that stores a string. If you want to use it, there's a header file you have to include. It's called just plain old string. This does not collide with the string.c that we learned about previously, because that would be called C string in C++. So this, when you include this, you get a new type named lowercase string. When you declare instances of this type, you can initialize them using the same syntax you would use for an array. So here I'm making a string A, and it gets a copy of the string 123 in it. When I'm making B, it gets a copy of the string XYZ. Here I'm making a string C. I didn't initialize it, but since it's an object, it automatically initializes itself. So I don't have to worry about it containing random garbage like a typical local variable would. Since it's an object, it initializes itself to be an empty string. Strings support value semantics in C. In C++. This string object, if you assign C to B, or if you copy B to C, C gets a copy of what was in B. So it gets XYZ in it, but that's a separate copy of what's in B. After you've done this, you could change the two of them separately. Comparing this to Java, since strings are reference types in Java, if you did an assignment like this, C and B would both refer to the same string. There'd be different ways of getting to the same thing. But in C++, this makes a deep copy of whatever's in B. Down here, well, I'm showing they overloaded the plus operator. So just like in Java, plus in C++ does concatenation for string objects. So A plus B would create a new string, 123XYZ, and then it would copy that over C. Well, erasing what I just did in the previous line. So this would overwrite what was in C with this new string. Internally, strings are implemented with help from a resizable array, like we learned how to implement. So internally, the string automatically allocates space so that it can hold a string that's as big as what you try to store in it. With operations like this, you don't have to worry about buffer overflowing in the string. Because it's an object, it knows how to automatically allocate space internally whenever you try to assign a bigger string to it. I mentioned that strings support value semantics, and that means, well, like I did on this previous slide, you can assign between strings, and when you do that, you're copying strings, unlike Java where you're just making strings refer to different things. And you can use value semantics when you pass strings to a function. Here I made a function f. It takes a string as a parameter. Down there in the client code, I make a big string and I call f, passing the string to it. And since I didn't say anything otherwise, this function f is going to get a copy of the string that you passed in, kind of like I'm showing here on the right. Inside this function, if you modified the string, and you can do that in C++, you're not changing the caller string, you're changing your copy of that string. What if you didn't want a copy? What if you wanted behavior that looked like Java? Well, you've got references for that. You could have passed a pointer to the string, or this might be a good job for that reference syntax we talked about. Here, instead of copying the string, I changed f. So it takes a reference to a string, but it promises it won't change what that string refers to. Because I marked it as const inside this function, if I tried to change what the string refers to, or tried to change the contents of the string it refers to, the compiler would complain. And in the caller, I don't have to change my code at all. Backing up here, when I took a copy of that string, when I passed the string by value, I just passed s to the function. Here, even though I changed the function, so it takes the string by reference, the client code doesn't have to change. So here, this is a point I tried to make earlier. When you're defining a function, you pick the semantics you want for parameters. You can either pass by reference or pass by value or pass by pointer if you want. And as long as you're just passing by value or reference, the caller doesn't have to change their syntax at all. They don't even, arguably, they don't have to know what's happening. So the caller, the client code, the person writing the client code doesn't have to be as smart as they do in C, where you have to know, should I pass this thing by address or should I pass it by value? Questions? I got more slides on strings, so there's more stuff I can tell you about what you can do with them. They overloaded the operators. They call them, I think, the extraction and insertion operators when you're using them for I/O. So you can write strings to an output stream. You can read them from an input stream. And just like with scanf, when you read into a string like this, it's trying to read a single word. So it skips white space and reads non-white space characters, and it stores them in Word. But you don't have to worry about buffer overflow here, because when they overloaded the extraction operator for strings, they were smart enough to make that string allocate as much space as it needs. So it will grow but depending upon how big the word you're trying to read is. I find that pretty handy. It's harder to make mistakes like that. There's a getLine function that I find awfully handy. This is a lot like what you did in Project 4, where you wrote your own function that reads in a line of text and allocates as much space as needed. But C++ already has a function like that. If you call getLine and give it a stream you want to read from and a string to read a line into, this will read the next line of input into the string, allocating as much space in the string as needed, modifying the string as it reads. So even though maybe you don't have to worry about this, this string and this function must be passed by reference. Otherwise, this function wouldn't be able to modify it. I may not have to think about that much when I call the function, but when I call this function, this line parameter is being passed by reference. Inside the function, it can change what's in my line variable. It can store the string in that, store whatever line gets read in that string. And like I started to say, this returns true or false. It returns true as long as you successfully read a line. kind of like the function we wrote. So if you wanted to just read all the lines of an input file one at a time, you could keep calling this function as long as it returned true. So here I'm trying to show stuff you can do with a string. They overloaded the relational operators so that they compare strings, and they do a deep comparison on strings. So if you say, does A equal B? That'll evaluate to true if those two strings contain the same string. You don't have to call a method to do this. I know in Java, if you want a deep comparison of strings, normally you call the dot equals method on one of them and pass the other as a parameter. But here you can use the equal equal operator or any of its friends like not equal. Less than compares strings lexicographically. So if A comes before B in lexicographic order, this will evaluate to true. So that's kind of handy. Strings, like I said before, they have methods. In C++, we'll call those member functions. That's what they're called in that language. And that's sometimes a trick of moving between languages, is adapting the terminology you use for that language. So for C++, functions are plain old functions are called functions, just like they are in C. Functions that are part of a class are called member functions, but it's the same idea as what we would have called methods in Java. For member functions, there are two ways of calling them, depending upon whether you've got an instance of that class or a pointer to an instance of that class. Just like in C, when you're accessing fields of a struct. If you had an instance of a struct, you used dot to get to its field. If you had a pointer to an instance, you could use arrow to get to its field. Same thing for calling member functions. All strings have a length member function. I think Java does it the same way. If you want to call length on an instance of a string, it's just dot length. And since you're calling a member function, you put parentheses around the parameters. This one doesn't take any parameters. So here I just left the parentheses empty, just like you would have in Java. If I had a pointer to a string, arrow length would give me the length. I'll go ahead and say, unlike string length, you can count, unlike the string length function from C, you can count on dot length being efficient. It doesn't have to go through the string and count the number of characters. It stores that probably as an integer internally in the class, in the string. So it's okay to write a function like this, or sorry, to write a loop like this, that loops through all the characters in a string up until we get to the length of that string. I mentioned weeks ago that if you wrote code like this using string length, strlen, on a char pointer, this would be a really inefficient way to write it because it would run in n² time. But in C++, this runs in linear time. So this is an okay way to iterate over a string in C++. In C++, they overloaded the square bracket operator so that you can use strings using array syntax. Strings are not arrays. They are an object. They're a class. But just like you can overload other operators, you can overload the square bracket operator, and they already did, so that if you say a bracket I, you're asking for the ith element of string A, just like you would for an array. In Java, you would call .char at here, and this does the same job. It's just the syntax is a little bit shorter and maybe more simple if you want to think of that string as an array. I guess another advantage is they used that return by reference trick that we talked about earlier. So this square bracket operator doesn't just return a char, it returns a reference to a char. If you want to just use that reference to access the char, you can print it out just like this. So you can use it just like it was a char, but you can also assign to it. So assigning to element 0 of a string will change the 0th character, in this case to an X. For that to work, the string, so that doesn't allocate space for you. If you want to assign to element 0, there better have already been a character in element 0. Otherwise, you're still buffer overflowing that string. But if you just want to change the first character to something else, you can do it with an assignment like this. So the point I kind of skipped an important point here. Strings are modifiable in C++. In Java, they're immutable, and that's kind of an important part of the design of how strings are supposed to work in Java. In C++, by default, they're not modifiable. If you want an unmodifiable string, you can always mark it with const to say, here's a string, it does everything a string does, but don't let me modify it. But unless you say that, strings are going to be modifiable. So here I'm showing you can use assignment to change any of their characters, to kind of sneak in and change what's in that string's representation. They even overloaded the plus equals operator so that it efficiently appends to a string. And you can append either an individual character like I'm showing here, or you could append a whole other string if you wanted. So plus equals will grow a string. So whereas here I tried to make the point, well, if you're assigning character 0, there better already have been something in character 0 or your buffer overflowing. Down here, well, this will enlarge the string as you add stuff onto it. So if you add a character to a string, even if the string was previously empty, it'll grow the string to accommodate the new thing that you're adding. We've seen one member function for a string, one method for a string. Strings have several methods that do handy things. I'm listed a few of them here, not nearly as many as Java has. If you look at the string class in Java, it's got a huge number of methods. String in C++ has a useful collection of member functions, but not as big as what Java has. There's a substring function that'll give you just part of a bigger string. Good, I gave myself a hint down here. It takes 2 parameters. Where do you want the substring to start from, and how long do you want the substring to be? There's an insert method, an insert member function that'll let you insert any substring you want, starting anywhere in the string. So this slides everything else down and inserts a new substring that you give. There's a function find that I'm showing at the bottom of the slide for finding a substring in a bigger string. Just like you can insert something into a string, you can erase a region of a string if you wanted. And this gets rid of all the characters from a given position for a given number of characters, and it slides everything after that down to fill in the space. So this shortens a string, whereas insert can enlarge a string. Both of these operations could be expensive, because if you had a big string and you insert something in it, everything else has to get slid down. Or if you erase, everything after that might have to get slid forward. Questions about this before we move on?
So I know I asked a question about being able to like do the cleanup that we talked about last lecture when things go out of scope. So
yeah.
Does C++ allow you to make your own like overriding for the operators? Like if I made my own class, could I change what addition does?
Absolutely. You can't overload every operator, but that's kind of, so the people who design string, they're using the same set of tools you have. And whatever string does to make itself look like a built-in part of the language, you can do that yourself. And we'll talk about that next lecture, at least that's the plan. So next lecture, we'll talk about what it takes to build a class that looks just like a primitive type, if you want. I mentioned in C++, C-style strings are still there, and they kind of inevitably, they show up in the language because C++ is an extension, mostly an extension of C++. So it kind of means we've got 2 types of strings. We've got the string object, and we've got char pointers or char arrays. And in the language, they've built in some stuff to try to make it easy to move back and forth between them, or at least when they define string, they tried to make it easy. If you think about this syntax or this code up near the middle of my slide, I make an empty string B. It starts out containing empty string, and then I assign it to the string 1, 2, 3. Well, you already know that 1, 2, 3 evaluates to a char pointer, just like it did in C, and it still does. But they've overloaded the assignment operator. so that you can assign from a char pointer to a string, and it does what you would expect. It takes a copy of the string that char pointer points to, and it copies it into the destination. So here, B, whatever was in B is going to get replaced with a copy of the 1, 2, 3. And if that means B's memory has to get enlarged to hold that, the string will take care of it. Its overloaded operator is smart enough to do that. When they created string, they made a constructor that takes a char pointer as its parameter. And when you create a string, like I'm doing down here at the bottom, if you pass in a char pointer as the parameter, and sure enough, that's what this quote ABC evaluates to, the string gets created, initialized with a copy of that. Here at the bottom, I'm actually showing a way of calling the constructor to make a new value of type string. Previously, when we called the constructor, we would make a new variable of type string, and then we'd put the parameters to the constructor after that variable. Here, I'm not even making a variable name. I'm just saying, make me a string, and initialize it with this char pointer. And this will create a new string. I didn't bother storing it in a variable, but you could use this string value anywhere something was expecting a string. Like if you wanted to pass it as a parameter to a function, you wouldn't necessarily even need to make a variable to hold that string value. You could just make it using this syntax and then pass it straight to a function. Usually, when you're going from a old style string, a char pointer or a char array, to a C++ string object, they design the object to make that easy. When you're going the other way, like sometimes if you've got a string object and you want to get a char pointer representing that string, you have to write a little bit of extra code to do that. And this is typically how you would do that. Every string object has a C_str member function. And here you can see I make a string str, I initialize it to ABC123, and then I take that string and I call this C_str function on it. That returns a pointer to a C style string, a char pointer that contains the same thing as the string itself. Really, it's returning a pointer to the internal representation of that string. It's kind of letting you sneak in and see how that string is stored. And the reason I say that is if you took a copy of that pointer and then later you changed what the string contained, what that pointer pointed to would change. And it might not even be valid anymore if the string had to resize itself. That char pointer might not point to the memory of the string anymore. So be careful about this. Don't destructively modify the string after you've called CSTR, or at least not while you're still planning to use that pointer. Why would you need to go from C++ to plain old C? If you were going to call something like printf, like if you wanted to print out the value of a string using the older function, %s in printf only knows how to print from a char pointer. If you had a string str and you wanted to print it using %s, you got to go get the internal string stored in that str, and that's what this member function is for. Here we've been looking at strings, and I find them awfully handy. C++ has a large collection of objects that do the same kind of thing, but for storing more than just a sequence of characters. I already mentioned the standard template library holds data structures. It does a bunch of things, but it holds data structures that, kind of like Java's collections framework, organize any type of data you want in various ways to make it easy for you to use existing data structures without having to rewrite them. Without having to rewrite them yourself. The STL, the standard template library, contains pre-built data structures that implement essentially resizable arrays, kind of like Java's array list, linked lists, double-ended lists and queues, heaps, balanced binary trees, a whole bunch of stuff. So if you're programming in C++, you still can implement your own data structures, but often you don't have to if you're willing to use one of these pre-built ones. All of the standard template libraries are all the data structures in the standard template library in the STL. They all use a template so that they all use a type parameter so that you can use these data structures on whatever type you need to. They all contain member functions for doing typical things, figuring out how big the container is, looking at its elements, and they use the same idea as Java here. They provide an iterator for letting you look around at what's in a container. We'll see that, but first we'll try to get by without needing that for a moment, using one of the simplest and most reusable containers, the vector. In C++, the type vector is kind of like array list in Java. In fact, in Java, if you rewind a whole bunch of years, they have a type named vector that is almost the same idea as C++'s vector. But the first time they did this, they made some design mistakes. Vector is still out there, but it's not the type you would normally use in Java today. That's why array list is called array list, because they had to pick another type name when they kind of redid how a resizable array was gonna work in Java. In C++, vector is still the way you would normally use a resizable array that you didn't want to implement yourself. So you can think of this as a class that's a wrapper around a reusable, resizable array. If you want to use it, you need to include the header file vector. Like I said, this is probably the STL container that gets used more than anything else. Kind of like in Java, array list probably gets used more than any of the other collections framework containers. Vector is a wrapper around a resizable array. And like I said, it takes a type parameter that lets you specify what you want it to be a vector of. So if you want to make a vector of ints, well, you say the type name vector, and then just like we did when we were using that exchange function, you can supply a type parameter inside angle brackets. So I want to make a vector of ints, and I want it to be named iList. So this is a variable declaration. This makes a new variable iList that has as its type vector of ints. And it starts out empty if you don't initialize it otherwise. So even if it's a stacked variable, vector being a class, it has a constructor, a default constructor. And if you don't specify any parameters, it will at least start out initialized as an empty list of ints. On the next line, I'm plugging in a different type parameter. So for dlist, I'm making a vector of doubles, and it also starts out empty if you don't say otherwise. Just like we talked about with instantiating parameterized types, when you make iList, the compiler looks and says, oh, do I have a copy of the vector class with int plugged in all over the place? And if not, it creates a copy of that class with int plugged in. Same thing when I make a copy of it with double. If it hasn't already done so, it initializes a vector with double plugged in as the type parameter. When you make one of these objects, you're calling the constructor for a class, even if you don't put parentheses at the end. The default constructor gets called. It has, kind of like Java has, it has a way of building an object with no parameters. And even if you don't put the parentheses, it'll call that default constructor. These types also have other constructors that let you specify how they should be initialized. If you pass in a single integer, you're saying how big you want that container to start out. So in this top example, I'm making iList, and it's going to start out with 10 elements rather than starting out empty. And for every type, it tries to use the default constructor for that type. Even for primitive types, C pretends they have a default way of constructing themselves, and it just initializes them with 0. So that's what it treats as their default constructor. So in that top example, that makes a vector events, an integer list with 10 elements, all of them initialized to 0, even though you didn't say you wanted them initialized to 0. If you want to pick a particular initialization value, there's a 2-parameter version of the constructor where you can say the size and what you want them each to be initialized to. So the second example makes a vector of shorts. It starts out with 20 elements, all of them initialized to 0. After you've made a vector, you're not stuck with its initial size. You can still add elements to it. And that's what the dot pushback member function does. Here, after I've made an integer list with 10 elements, all of them 0, I run a loop that pushes 10 more elements to the end. And because I'm using the loop control variable here, it's going to push a 0 onto the end, then a 1, and all the way up to 9. So when I'm done with this little piece of code, iList is going to have 20 elements. The first 11 of them are going to be all zeros because I push a 0 here at the start. And then the remaining 9 of them are going to count up 1 to 9. Pushback is kind of like .add in Java. Here, the syntax is a little bit longer, but it adds a new element to the end, growing the vector as needed. So here you're getting that resizable array behavior. Just like string, with vector, even though it's a class, they overloaded the square bracket operator so that you can use a vector as if it was an array. It's not an array, but it looks a whole lot like an array syntactically. All containers in the STL have a .size member function, and I'm using that here. So vector, all the others that we're not going to talk about, they have a .size, just like Java has for telling you how many elements are in that container. And like I started to say, they've got vector has an overloaded square bracket operator. They don't all have this, but vector does. So you can use that to look up the ith element. And just like with string, it returns by reference. So you can use square brackets to look up an element and then use it, or to look up an element and then change it. In Java, if you want to change what's in an element, you have to call usually a I can't remember if it's .set or .put to change the value of an element. But in C++, you can use the same syntax. You can look up the ith element with square brackets and then assign to it, even using all the versions of the assignment operator that you want. So times equal works just as well as equal. Vector has, like we showed here, it has a pushback method. It has a pushback member function for adding things to the end. 2 slides ahead, it's got a popback method for removing things from the end. So vector, just like any resizable array, it's efficient to add and remove stuff from the end because that's the end that the container grows on. So .popback removes an element from the highest index, shortening the container by 1. So this sample code would go through and print everything in iList backwards, starting from the last element. Popback does not return the value that it removes. So some of that is just for efficiency. If you don't need the element, then returning it would require a little bit of extra code, and it would use up a little bit of extra stack space temporarily. So if you want to use the element you're going to remove, like I'm doing here, you better use it before you remove it from the container. Pushing and popping at the end are efficient. There are other functions, other member functions to let you insert and remove elements anywhere. But they could be less efficient because just like with strings, if you insert a value in the middle, someone's got to write code, or internally, everything has to be slid down from there. So that's more computationally expensive. You can do it. You just need to be aware of the expense. There are also handy built-in member functions for getting a reference to the first and the last element. I think they're .front and .back. If you need an easy way of getting a reference to, again, the first or the last element in a vector. One more thing I think we can afford to cover today, and that is, just like string, vector supports value semantics. which means if you make a vector, you can copy it to another vector, as long as it's the same type, using assignment. So the code I've got up at the top makes a copy of an existing list to another list. You can pass a vector to a function by value if you want, and then that function gets a whole copy of the vector, which is handy if you want to make a copy. If you didn't want to make a copy, this is extra overhead that it would be nice to avoid. It's easy enough to avoid using the tricks that we already know. You can just pass a vector by reference if you want to let a function use it, but you don't want to copy it. So this would be more like this top example would be more like what you get in Java automatically with a container. If you don't want to copy it and you just want the function to be able to use your vector, you can pass it by reference. If you want the function to promise it's just going to use your vector, but it won't change it, you can always put a const on that. And then this is an efficient way of letting the function use your vector, but with the safety advantages of pass by value. The function promises it won't sneak in and change your vector. This is enough to let you use vectors, but for next time, we'll have to save iterators, a way of efficiently moving around a vector without depending on an integer index to do that. We'll save this for next time. I'll try and talk a little bit faster next time because I'd like to cover as much C++ as I can, but I think that's all we can manage to cover for today. Thanks for your attention. If you have questions, hang around and I'll answer them. Otherwise, I'll stop recording now.